Okay, so welcome to the simplified explanation of Lenz's left-hand rule slash Lenz's law. I find the whole left-hand rule part of it to be quite confusing because, in my opinion, it just doesn't make much sense. Especially, if you have to switch your hands, it just doesn't make sense to me, and I have never been able to comprehend it in the way that our teachers explained it. So what I came up with as a way to think about it is to think about it as a coordinate grid. So, on a coordinate grid, you have your four quadrants. Your quadrants are Q1, Q2, Q3, Q4. Now, each of these quadrants responds to X and Y, as in the X plane is moving in a certain way or the Y plane is moving in a certain way. In quadrant one, they're both moving positively. X is moving up, Y is moving right, which is shown here. Now, if you have a magnet, that is, let's say it's south north, and your current, or sorry, your magnetic force is going this way, and you have a conductor that's going, I think it's up in direction, that's how you can think about this. It's going up X and right Y, which up X, right Y are both positive in this situation. So you're going to be getting a current opposite of what your induced voltage will be negative if your regular voltage is positive. Now, if you think about it in the other way, where you have it going, where you have um, your current is still going south to, or your field is still going south to north, but instead your conductor is going down, which is down here, it would be a negative and a positive, which I explained here as well. If you take a negative times a positive, it gets you a negative. Same thing as, a positive times a negative. Compared to two positives always come out to positive, and two negatives always come out to positive as well because of the double negative rule. So in this situation, because your induced volts are technically negative of what they're supposed to be, if if we were doing it in say this format, then it would be positive volts induced. So that's kind of the way that you can think about it. Yeah. So in this situation, your conductor would, like, every time that you induce voltage, it is opposite the polarity of the force producing it. So if we're going down and our polarity is, say, south or something, or if our polarity is negative, then the induced polarity would be positive because that's opposite. The same thing goes for quadrant two, which is also a positive and a negative, which always gives you a negative. Just, the field is flipped and the conductor motion is flipped. Whereas Q3 is the same as Q1, which always comes out to positive, aka the opposite of your induced voltage. Well, all of these are opposite your induced voltage. It's just if your voltage is below ground, is the way that we refer to it as. Um, like for example, these two, your voltage is below ground. So I'll write this. That's your ground symbol, as we went over in blueprint. So in both of these, your ground point is, or your voltage is moving below ground. So the way to think about it then is if it's moving opposite the force that you normally want it to go, which normally we want it to be going up and right, because that's how sine waves work. Like let's see, yeah, okay. So say we have this here. We have a sine wave like this. Obviously, as we go along, we want it to go right, and if it's going up, then it's positive. If it's going down, it's negative. So that's how you can think about this. If the conductor is going up, then it's moving in the quote unquote right direction. And if the current is moving, or if the field is going right, then it's moving in the right direction. So that's why we want this, is because it comes out to a positive. But running in the opposite direction both ways still works as well in giving us positive. So I know that this is definitely a little bit cluttered, but I think that what I mean to say is coming through. So instead of worrying about, which way your thumb and your fingers are going, you can think about, is my is my field going right, and is my conductor going up? Because if your field is going right, your forefinger, your index finger, your first finger, if that is going right, then that's the same as your field going right. However, if your thumb is going up, then that's your thrust. That's the movement of your conductor. So essentially, this is the same way as the whole finger strategy, except I find this easier to comprehend because you don't have to worry about having your hands in the right rotation, or, which hand you're supposed to use. It's just thinking about it in math terms, which I understand can be complicated, but I feel as though a coordinate grid is a pretty simple way of thinking about it. So let's do a quick practice here. So say we have a magnet set up like this. We have our current, or we have our field going this way, and our conductor going this way. So now think for a second. Would this be a negative voltage that would be induced, or would okay? So the voltage coming through here, the whole thrust thing, is this going to be a positive or a negative voltage? And then you have to think about, is the field going right or is it going left? If it's right, then it's positive. If it's left, then it's negative. So if you think about it, going this way is negative, this way is positive. So, and that's, how magnets can be labeled as well. They can be north or south, they can be positive or negative. But because we're going negative with our field, that gives us one number negative. But because our conductor is moving down instead of up, that gives us two numbers negative, which comes out to a positive induced volts, or negative volts. So the thing to remember, especially when using this method, is your induced voltage is always going to be 180 degrees out of phase with the voltage that causes it, which what that means is your induced voltage is always going to be it should always be opposite of the voltage that induces it, is what I should say. It might not be, like, oh, this one is 10, so the other one must be negative 10. I'm not sure if that's the case. I can't speak on that. What I can speak on is, if the voltage causing it is positive, then the voltage that reacts is negative. However, if the voltage that causes it is negative, then the voltage that reacts is positive. So, for example, yeah, the voltage causing this is negative, but, well, is that how I want to say that? I don't think that's how I want to say that. Okay, disregard that. I think the best way to explain it is just, the whole coordinate grid thing. If it's up and right, it's right. If it's down and left, it's right in a wrong way. But these two are both wrong. You know, to think is a way to think about it. They're both producing a voltage that theoretically would be the same polarity as your current voltage that's causing it, which we don't really deal with that very often, I don't think, because that's not the point of an inductor. Um, Compared to, if it's going up and right correctly, then, it'll cause uh, the correct induced voltage. Um, yeah, I think I have explained it as best I really can. It's definitely a tricky subject to get a hold of, but I hope this helps clear up a little bit of the fog. Um, yeah, obviously the finger rule really helps explain the how or the reasoning why, but I feel like using this coordinate plane system explains it like in a much simpler way where you don't need to worry about which direction your fingers are pointing. If you need to like turn your hand upside down and to the left or whatever and hurt your wrist or something, if you think about it this way, it still comes out to the same thing, just without as much physical work, a little bit more mental work. So, um, in general, yeah, I think this is a much simpler kind of concept, be or a much simpler way to think of the concept. But everybody has their own ways of thinking about it. But yeah, if this helps you out, let me know. I would be glad to help develop some alternative angles to look at things if this helps people out. But yeah, that'll be it for now. I hope you enjoyed the video, and I will see you around.